I'm going to be talking about structured ML and structured ML in particular in the context of challenges and opportunities for the SysML community. But first I need to unpack what structured ML is. So we have structure, and I'm going to be talking about structure in both the inputs to machine learning algorithms and also structure in the outputs of machine learning algorithms. And then I'm going to tie this to both opportunities for systems for structured ML and ML for systems. But let me unpack a little bit what structure in the inputs is. You know, the data that we have today has all kinds of crazy structure. So it's multi-relational, there's different kinds of entities, they're interacting in all kinds of crazy different ways, there's spatial temporal information, and more. It's linked and all these kinds of things. But then in addition, in many of the kinds of algorithms we want to do, even the basic ones like, our basic sounds derogatory, you know, the important ones like natural language processing, computer vision, things like science, computational biology, there's all kinds of structure. And I like this quote from Dan Roth. He says, you know, all interesting decisions are structured. So they have, you know, little components that you're making decisions, and you need to, you know, what you decide in one place for, you know, the part of speech for one word will influence what the part of speech for another word is, and what you decide for one object in the image influences what you should infer the other object in the images, and so on. But I would say that most of our machine learning algorithms right now take this kind of nicely structured data, this is my cartoon of it, and they flatten it and they put it in this matrix form. And this matrix form then is really convenient. I can feed it into my machine learning code and so on. But there are a bunch of really important issues with this. So one of the most important issues, and this was an issue that Mike this morning brought up, is it's actually making very often very, very, very incorrect statistical assumptions about the data. So it's assuming that the data's IID, and most data that you get are, probably would say all data that you get in the wild, in the real world, you know, it's not a nice, clean, random sample that's been cleanly generated. And that bias, if you don't take that into account, you have serious problems with your algorithms. And, you know, maybe it's not such a big problem when you're doing it for something that's not impacting your life directly, but when we're starting to take these machine learning systems and placing them in these intelligent infrastructures, it really is important. It also doesn't support collective reasoning. So collective reasoning is this dependencies between the outputs. And so there's something fundamental. Once you've broken it into the rows, you're saying the decision that you make, the prediction you make for each row doesn't affect another row. And again, that's a place where you're losing opportunity to exploit the structure. And then the third piece I think is particularly interesting for the SysML community. It's not declarative. When you do this flattening, usually you have some procedural code that you're using that you throw away, and that actually oftentimes is the place where most of the computational effort goes in, doing all the crazy weird joins and aggregations and other projections that you're doing to put it into this matrix form. On top of it, because you've lost the declarative nature of the feature construction, that's one of the places where you have the biggest opportunity to optimize. And so if you don't have that kind of coded in a way that you can really keep track of, that is a problem. So I think we need machine learnings that take into account structure. And in this talk, it's a short talk. I'm going to quickly kind of provide some examples, so some patterns for using structure, go into a little depth of a tool, and then some templates for structure. But I'm also going to be doing this in a way that I want to identify both opportunities and challenges for the SysML community. And those are going to kind of come up after I say a little bit more about what I mean by structure and define it a little bit more. So I am going to be doing both sides of the systems and ML part. So I'm both going to be talking about systems for structured ML. What are all the kind of cool things? Once you have this structured approach, it really brings up, crazy opportunities for systems to exploit it. And then also, I think a lot of systems data is inherently structured, and these tools apply. So I'm going to go through kind of three parts of the talk. But the questions that you should have in mind from a SysML community perspective, where is the structure? And how is it expressed? And is it already being exploited? Are there new opportunities for exploiting it? And more. So the first thing I'm going to go over is patterns. And beware. So this part of the talk is very basic, but it's purposely very basic because these really simple structured patterns can buy you a significant amount in your machine learning algorithm. So we've oftentimes seen where we take some off-the-shelf classifier, we add in just a little bit of structure, and we get improvements of 10%, 15%, usually at least a couple percent, and percent in what, it depends what you're measuring. How am I going to represent that structure? I'm going to use logic. Logic has advantages for capturing the structure. It's also interpretable. And for anybody, so Mike was not so keen on logic this morning. Just wait 10 minutes in my talk, and I'm going to be connecting logic to optimization and so on. So bear with me. It's just, I think for this community, it's really easy to express all of this first in terms of logic. And the structured prediction patterns, we do tons of stuff. My research group does tons of stuff with graph data and network data. These are these canonical patterns that we found over and over again are useful. They're super easy, and I want to show you why they're structured prediction problems. The first is collective classification, and the basic idea is inferring the labels for nodes in a graph. And so how do I write that in logic? I have something where I have some local predictor that predicts a label for a node here. And then I also have the thing that makes it collective is that I say, well, the label of a node and the label of another node y, where there's a connection between them, there's some logical relationship between them. And this thing where you see what I'm trying to infer is the label, and the label occurs on both sides of the rule. That's the thing that makes it collective. There's this dependence happening. These unknowns are going to be connected in a certain way. And so this is an abstract version of it. Let me ground it in a simple motivating problem. So I have a network. I'm trying to infer political orientation for people in this network. And usually what happens in these settings is I do have some labels, and then I have some nodes that are unknown. So already you can tell this isn't a regular independent classification problem. How do I encode this? Well, I can encode things like I can use whatever local information I want. So I can have these rules that say intuitive things like, okay, if someone donates to a particular party, they're a member of that party. I can say something about, well, if their social media uses keywords that are connected to a particular party, I can infer something about the label. But then more interestingly, the structured part of it is that I say something like, well, if they vote for a party and they have a friend, then their friend is more likely to vote for that party. Likewise, I can use other relationships, so spouse and so on. So this shows an example of an incredibly simple structured dependency. The next structured dependency that comes up all the time in graphy, networky kinds of problems is predicting edges. So inferring the existence of an edge in a graph. Now, the kind of template for doing this is, well, if I have a link between x and y, and I have some other z that's similar to y, then I have a link between x and z. And again, you see the fact that you have the unknown, the link, that's the thing that I'm trying to infer on both sides of the rule, that's going to make there be dependencies between these things. And let me go through, the canonical example of link prediction is a recommender system, where in a recommender system, you have things like, if a user likes an item and there's another item that's similar to that first item, then they're more likely to like that second item, and vice versa. If a user likes an item, two users are similar, then the second user will like that item too. So, these are the classic patterns that one uses in recommender systems. And you see that there's these things that you're trying to infer on both sides. And then finally, the last pattern that I want to mention is entity resolution. So entity resolution is the problem of figuring out which nodes in a graph refer to the same underlying entity. This problem is ubiquitous in computer science. It comes up all over the place. The interesting thing from a structure prediction setting is one way of encoding this is, you start off with some local information that says, okay, well, if they have similar references, if they have similar names, if they have similar context, they're likely to be the same. But then you often also have a kind of transitivity rule that says, well, if x is the same as y is the same as z, then x and z are the same. So sometimes you're doing a kind of clustering problem where you're solving this. But there are also entity resolution problems or deduplication kinds of problems where you have a different form of the constraint. And the different form of the constraint is a matching constraint, where it says that, if x and y are the same, then, and y and z aren't the same, then x and z can't be the same. So this is essentially a mutual exclusion kind of constraint that says I can only match to one of these things. And it's really important when you're doing entity resolution to know which setting you're actually in. And so you see these dependencies again. So these are simple structured patterns. Just adding them into your vanilla classifier can buy you a lot. Most of the problems that we look at, do all of these at one time. And you can imagine, if you try and do all of these at one time, it makes the problem much, much more challenging and, all kinds of crazy dependencies between things. So logical rules have advantages, but they also have major disadvantages. What are the major disadvantages? We all know that dealing with logic is intractable. You can't, once you have an inconsistency, you're dead. And actually, some of the problems when I was talking about them, I was talking about more kind of similarities rather than kind of 0-1, true-false kinds of things. So I'm next going to introduce a tool that addresses these issues. And this tool comes from the bigger area of statistical relational learning. So there's a whole field, there's a whole bunch of people that have developed tools over the years, languages over the years, probabilistic programming languages. I'm going to dive into specifically ours, which very much builds on those, but I think we found a really sweet spot in terms of tractability and scalability and expressivity. And so our tool is called Probabilistic Soft Logic, PSL. No, that is not pumpkin spice latte, but if that helps you remember it, that's okay. It really is that you have a collection of rules, you have some input data, and that's going to define a program. I'm going to tell you what the semantics of the program are. It gives you some probabilistic semantics. But if you want the gory details, go to this JMLR paper. And if you want the code, it's open source. There's tutorials, data sets, all those available at this link. One of the things that makes PSL unique, and I think very interesting from a SysML perspective, is one of the differences between it and many of the other approaches is the random variables we're going to introduce are not 0-1. They're not logical variables. They're continuous between 0 and 1. This is going to allow us to convert logical inference into convex optimization. So Mike had said he doesn't like logic, he likes optimization. See, we're going to do optimization after all. And this allows us to have a tractable system, deal with inconsistencies, and represent similarities. For the foundations, I'm going to give an overview of the foundations. This is very much work of Stephen Bach, who some of you know. He's a postdoc currently with Chris Ray's group. He was a PhD student with me. And he was the one that was really behind finding this kind of key idea, connecting this concave maximization. And I haven't explained it to you, but take this and kind of brand this in your brain, the structure of this. And the neat thing is this comes up from properties that come from the theoretical computer science community, properties that come from the machine learning and statistics community, and properties that come up from the AI community. And under all of these three different interpretations, you actually get a function that looks like this. So I'm going to attempt to go through this quickly, but we're going to go from randomized algorithms to graphical models to soft logic. And for the randomized algorithm, we all know we have some collection of rules. So some weighted logical rules is where we start. So we have non-negative weights. These are the positive literals. These are the negative literals. And we're going to put it in this disjunctive form. And then what we want to essentially do is solve the weighted max-at problem. And we also all know this is NP hard, so that's not good. But we can change the interpretation for the random variables. Instead of having them be logical variables, we're going to convert them to rounding probabilities. Probability that I round up to 1 or down to 0. Then there's this very nice result, old result from Goemans and Williams from '94 that shows how to bound the expected score for this weighted max-at problem. And now, in addition, it gives you actually a approximation bound on it, so a 3/4 optimal approximation bound. And if you look at that formula, you guys all memorize the formula that I had a few slides ago. It has exactly the form that I had before. So that's one interpretation. The next interpretation comes from the graphical models community. And so from the graphical models community, I can formulate this whole set of weighted rules as a factor graph. And the factor graph, I have random variables, I have the rules. The rules actually are going to be potential functions. And so the potential functions are a particular form of potential function that correspond to these logical rules. And now I can define a distribution. So this is a factor graph distribution defined the weights times the potential functions. I'm going to sum over all the instantiations and the different rules. And map inference is finding the assignment of the random variables that maximizes this probability. Unfortunately, doing that is intractable, so we're going to look at ways of approximating it. The classic way of approximating this is using variational inference, where variational inference, what we will do is we're going to attempt to find a consistent set of marginals. And if we found a globally consistent assignment of those, then we actually would have a solution to our problem. The only problem is you have exponentially many number of these constraints, and so it's intractable. So what people do very commonly in the machine learning literature is they use something called local consistency relaxation. And the basic idea, I'm going to show it more with a picture, but I want to reference very, very active area in graphical models inference. But the basic idea is you have these exponentially many constraints. We're going to relax some of them, leave some of them off, and then solve it. Now, in the context of the models that we're looking at, what Steve was able to show together with my postdoc Bert Wong is we can take these pseudo-marginals. We can also introduce pseudo-marginals over joint states of the variables, and then push in this optimization. And the result that they were able to come up with is, and this required some kind of analysis of the actual optimization problem, they were able to show that this is the way that you can express it in terms of just the mu variables. And again, if you look at that, that actually has the same form as we saw before. In particular, they did some more analysis where they compared to kind of dual decomp methods and so on. And if you're familiar with those, this result from AI Stats 2015 is actually pretty interesting. But what we've done so far is we've done two interpretations that lead to the same optimization. And the cool thing from a machine learning perspective is we have a approximation guarantee from the theoretical computer science community that we can now apply to the graphical model setting, where the graphical model setting, everybody was doing these relaxations, but they didn't have any approximation guarantees. The last one that I want to mention is coming from AI. And in this case, we're looking at now really interpreting these random variables as degree of truth. And we're going to use a well-known, but not the only, framework for reasoning about soft truth values, where they define the disjunction and conjunction and negation in a particular way. And it turns out, if you do a little bit of algebra, doing the exact solution, so now we're not doing any approximate solution here at all, the objective ends up looking like this, where we're maximizing, we're trying to find the assignment to the random variables that maximizes the probability. And you can think of the term in the middle here is like how satisfied the rule is. And so that's, before you just had 0, 1, is it satisfied or not? Now we have a term that's, how satisfied is it? But again, this has the same form. So cool. So this one formalism can allow you to reason scalably under these 3 different interpretations. Now, we expanded this to define what we called hinge loss Markov random fields. These add in some modeling capabilities, so you can add in hard constraints and so on. And now a PSL program, in particular a PSL program like that voter prediction one that I gave at the very beginning, looks kind of like this. So I write out these logical rules and so on. That's what the program looks like. But the kind of semantics for it is that I have the program, and then I have some data. And the program together with the data defines a big distribution. And I'm able to go from combinatorial optimization to convex optimization. That's huge. Now I want to make it even more scalable, because a large graphical model is still challenging to solve, especially the ones we're constructing. They're crazy, loopy, so on. So what we can do is we can kind of look at the structure of the potentials, and we can exploit these. And we're going to use a particular convex optimizing approach called ADMM, which folks, a lot of you will be familiar with. There's a reference to Boyd on doing this, but it's known to converge for convex problems. The trick for doing this for PSL is actually those potentials. We want to go and be able to solve each of those little pieces really fast. And this was partly you need to break them down into even more structure, so that you have these kind of areas where the potential is satisfied, and then you have this kind of linear loss where they're not satisfied. Once you do that, you can really speed things up. And so these empirical results are very much due to my student, Eric Augustine. Eric, where are you? Okay, here. So these are comparing CVXPy, which is a well-known optimizer, MOSEC, which is a commercial grade optimizer, versus our implementation of ADMM. And what this is saying is, for something that has 150,000 potentials, which for a graphical model is relatively large, understatement. So CVXPy can do it in 3 hours, MOSEC can do it in 3 minutes, PSL a few seconds. 500K potentials PSL can run in less than a minute. So that's great. But this was like 2 months ago. And so more recently, Eric has put in a bunch of systems optimizations. And from these systems optimizations, we're able to go up to 2 million potentials in less than a minute. So this is exciting. How well does it work? Well, some results on different kinds of problems. So this is a kind of standard one. A lot of our results look like this. This is an activity recognition and video problem where you use some simple local vision-specific features, and you don't do that great. You put PSL on top, and you are able to, even with really simple structured rules, improve performance significantly. Here's two results, one for a collective classification problem, one for a link prediction problem. Here, the key thing to note is compared to a discrete MRF, we're doing a little bit better, but we're also 2 orders of magnitude faster. And then a problem where we're combining similarities for computational biology. Again, we're able to beat state of the art. But the thing that I think is most impressive here is it's declarative. It's really easy. You get some additional information. You can add it into the program really easily. But now, from a systems perspective, what are the kind of key things? One of the things that happens is there's different ways of dealing with the grounding of these networks. So you have data and rules. And we're able to compare. And if you go to our poster, you'll get more details about this. But approaches where you're doing it either in the database or in the application layer for removing these kind of trivial potentials that are already satisfied. And it turns out that removing them at the applications level actually has significant advantages, especially when, because of the fact that that makes it very easy to parallelize. And another kind of result in this space where looking more at the systems level, how do we make it even faster? There's an important thing when you're doing these cross products. You want to block things so that you don't consider all possible values. Well, there's different ways of doing the blocking. The way that you do the queries for this has a big impact. And it turns out that, you know, doing a form of blocking, which we call implicit blocking, where you just, you aren't telling the system that these are blocking predicates. It really saves in memory usage, but the queries to execute it are expensive, versus by doing explicit blocking, providing hints, you both get the memory advantage and significant performance improvements. So this, I think, is a tip of the iceberg. I think there's a lot of interesting systems things that one can start doing when you have these. I want to mention applications where we've done a lot in computational social science, knowledge discovery, come talk to me. The place where I'm excited, especially in this community, is applications of these structured machine learning methods to systems data. And one example of this that we've been looking at is for load prediction and anomaly detection. So load prediction and anomaly detection either at the data center level, we have one project that's around wireless networks, another that's around looking at virtual machines and finding problems. I think there's a really interesting ability in systems to look at these structures. And this is only talking about the software piece. Like, then you get down to the hardware level, there's additional structure. We've also done some work on visitor stitching. So this is a problem of entity resolution. You're trying to figure out, okay, you have this person on the phone, you have this person on a laptop. Are they the same person? The kind of data that you get, the systems data that you get for that, how can you make use of it? How can you exploit the structure? And we also have a poster this evening. Johnny Chang will be presenting. And we've also done stuff in energy disaggregation. This isn't directly a SysML concept, and detecting malicious behavior. So to close, I want to start off with actually the most important part, which is acknowledgments. The best thing about working in this space is all the cool students you get to work with. I didn't get to mention all of my students and all the cool things that they're doing. All the companies you get to work with. So we have a lot of nice collaborations that are going through our data science center. And this makes it fun and grounds what you're doing. And I really think that, well, first off, hopefully I gave you unpacked what this structured ML is, and maybe excited you about the opportunities for the SysML community. But I think there's a need for this ability to mix probabilistic and logical approaches, and that it's really interesting from a systems perspective what you can do in that, and from a machine learning and an AI perspective what you can do. There's structure in the model, there's structure in the systems, there's structure in the hardware. So having a way of talking about that and doing things that mix kind of data-driven, plus you have some knowledge, have a way of declaratively representing that. And I think there's tons of applications in SysML. And my talk is challenges and opportunities, but I'm trying to focus on the opportunities. So if you want to see these as challenges, if that motivates you, that's fine too. All right, thanks.